Welcome back, everyone. In this lecture, we're going to focus on creating the actual model for the convolutional neural network on these custom images. And the model is going to be fitting to a generator. Let's get started. Okay, here we are in the notebook where we left off last time. Let's get to creating our model. We'll say from TensorFlow.keras.models, and just as we did before, we're going to import sequential, and then we'll say from TensorFlow.keras.layers import, and what we're going to do is we're going to import a dense layer. This is for the very end, plus we can add some dense layers after our convolutional layers. Let's go ahead and import our convolutional layers, that's conv2d, and then we'll also import our pooling layers. So there's max pool. A common point of confusion for students is what's the difference between max pool versus max pooling? They're actually the same thing, and you can check this out. If you go to the TensorFlow documentation, you'll notice a lot of these classes have subsections called aliases, which basically means there's multiple names for the same function call. So just keep that in mind. It's a really common, almost like an issue with TensorFlow, that due to the fact that it has so many versions, that there's a lot of aliases for the same thing, even within something like Keras. So we have both max pool and max pooling too. They're actually the exact same thing. So we're going to say dense convolutional 2D, max pooling 2D, and because this is going to be a bit of a larger network, let's also add in the dropout so we can prevent overfitting, hopefully. We'll say model sequential, and now it's going to be time to add in convolutional layers. So what I'm going to do is set up a base convolutional layer. So we first say convolutional 2D, and then we're going to decide to have 32 filters here. And I'll choose a smaller kernel size, something like 3 by 3. And then the input shape, and this becomes very important, the input shape should be equal to the input shape we defined earlier. So input shape is going to be equal to the image shape that we defined. So recall earlier, we defined an image shape based off the average size of these images, and that's what was up here. It's 130 by 130 by 3. And this is something you can play around with. Keep in mind, if you choose an image shape that's too large, especially if you're dealing with extremely large files, you may run out of memory on your computer. Again, that's really dependent on your hardware. Okay, so 130 by 130, those aren't too bad, so we'll go ahead and keep image shape there. And let's choose an activation function. We'll say activation is equal to rectified linear unit. And then after that, we will add in our pooling layer, so max pool 2D. And we'll just go ahead and keep the default pool size just so we can see it, so we can keep it in mind. It's 2 by 2. So let's go ahead and add in a couple more convolutional layers. The larger the image sizes and the more complex of a task you're dealing with, the more convolutional layers that you should probably have. And there's a link for you in the notebook. So if you check out our deep learning notebook and scroll down, there's a link here to a really nice explanatory post on different rules for selecting the number of neurons and number of filters in convolutional layers. So definitely check out that explanatory post. Okay, so the one thing I'm going to edit here is as we get deeper in this network, I'm going to create more filters. So we'll have these two kind of inside hidden convolutional layers have 64 filters each. Then after this, we will flatten out our model. So we'll say go ahead and flatten this out, add in our flatten layer, and it looks like I forgot to import it, so let me do that as well. So we'll say flatten, import that, and then I can call flatten here. So that flattens it out for our dense layer. So we'll say model add dense. Let's go with 128 neurons, and we'll say our activation is equal to rectified linear unit. Something I want to point out, and you may see this as you explore more complex convolutional models, you can do a lot of exploring online to see how other people kind of attack different data sets with different images of different sizes. You may see some people add in the activation after dense. So another kind of alias you can do, and I'll come back here to show you, is in our notebook, there's essentially an example of doing this in 2 steps, where it's you add the dense and then add the activation function after the dense layer. That's the exact same thing as what we did here, which is just calling it inside of the dense. So it's up to you which one you want to use. And then what we're going to do here as well is we'll add in our dropout. We're going to turn off half the neurons randomly to prevent overfitting. After that, we have our final dense layer. So we'll say dense1, and then say model, and whoops, you can add in the sigmoid function or just say here activation is equal to sigmoid. We also show the alternative method here, which is adding it after the fact. Either one, totally okay. So we have dense activation sigmoid. Last thing I want to show you is the compiling of the model. We'll say compile the model, loss. This is a binary classification problem, so it should be binary cross entropy. And then our optimizer will be atom. And optionally, if we want to check out the metrics, we can say metrics is equal to accuracy. Run that, make sure we have no errors. Okay, looks like our model is working. Go ahead and check out a model summary. So call summary on your model, and you can see the different layers, and you can see the different parameters per layer. Notice that we have a ton of parameters by the time we get to the dense layer, so this model will take a long time to train. To make sure we can pick the right amount of epochs to train for, we can say from TensorFlow.keras.callbacks, import early stopping, and then create, just as we did before, an early stopping callback. We'll do this based off monitoring validation loss, and we can have a patience of 1 or 2 epochs. That's something you can play around with as well. Okay, so that's creating the model. For training the model, we have to select a batch size. So we'll go ahead and train on batch size of 16 images at a time. So it's pretty typical, again, to choose something in the power of 2. So 2 to the power of 2 is 4, 4 to the power of 2 is then 16. And the larger your hardware, the larger the batch size you can probably reasonably choose. The smaller the batch size, the longer the training time takes because you're feeding in less images at a time. So what we're going to do is we're going to create 2 generators, just as we did before. And the generators will say train image generator is going to be one of them. And then the other one we're going to do is a test image generator. These are going to be very similar. The only difference is going to be the source of their data. And we already went through this on the flow from directory that we need to put in the training path. And there's a couple other parameters we're going to state here. So what we have to also state is beyond the directory, which we already have as training path, is the target size. So what is our target size? Notice the target size just cares about width and height. So what we do is we say that our target size is equal to the image shape that we defined earlier. So just to remind you, the image shape from earlier is 130 by 130 by 3. I really only care about those first 2 dimensions. So that's colon 2 to get 130 by 130. So that's what I'm going to pass in here. I could do this manually, or I can kind of set it off that variable. Next, I need to make sure my color mode is correct. So since I'm dealing with color images, my color mode is red, green, blue. If we come down here, we can see the different parameters. So it's either going to be grayscale or red, green, blue, or if you're for some reason dealing with an alpha channel as well, alpha is transparency, you can pass in RGBA. Okay, so there's our color mode. Last couple things we want to set here are the batch size. So the batch size is equal to batch size, and then the class mode is going to be binary because it's binary classification. I'm essentially going to copy this and then paste it for my test image generator. Go ahead and run the first generator. That one's ready to go. The things I need to change here is the test path should be for the test images, and you'll notice that one of the parameters here is this shuffle call. So shuffling essentially shuffles your data before it kind of makes this random batch of data points for you. During training, you should be shuffling your data. However, when you're generating for the test set, you don't actually need to shuffle. In fact, you shouldn't be shuffling. Otherwise, your labels will get shuffled around from your actual feature points. So we want to say shuffle is equal to false when running in test data. Okay, so that's our training image generator and our test image generator. And what we can do is now take a look at these objects. So for example, our training image generator, and we can say class indices, and it reports back that 0 belongs to the parasite, 1 belongs to uninfected. And then what we're going to do here is we can say my resulting model or results is equal to model.fitGenerator. We pass in our training image generator, pass in some number of epochs. You can choose a larger one here because what we're going to do is pass in our validation set. That's the test image generator. And then the callbacks will be equal to early stop. So we can go ahead and run that, and then that should begin training. Keep in mind, this is going to take a long time to train. So what I'm going to do is I'm actually going to interrupt my kernel, and we actually already have a file for you. Underneath convolutional neural networks, we have a malaria detector.h5 file. Let's go ahead and load that up to save some time. So you can, if you want, train your own model, especially if it's different than the one that we defined in our notebook. Or what you can do is say from tensorflow.keras.models, import load model. And what we can go ahead and do is say model is equal to load model, and then pass in malaria detector. I would highly encourage this, especially if you're running this on a kind of simpler hardware computer. Go ahead and load in that model, and to confirm that the model worked, say model summary, and you should see something that essentially looks like this, the model we just created. Except what's nice is this model has been fully trained. Something to note here is if you do decide to load our model, what is not going to be available to you is the model's training history. So if you tried model history.history, it's going to say it can't find it because it doesn't actually have it. That's because you loaded the model, and this is just saving the trained model. It's not saving the history of the training model. Keep in mind, you can optionally save the model history if you really want to. So if you just Google search save model history Keras, basically hit this first link, there's code here on how to actually essentially save this as a pickle file, the actual history of the training. But the reason we didn't save it is because we actually show you the history of the model. If you come to our provided notebook and scroll down, we will actually show you kind of the history here of loss validation plot. So you can essentially just see the history of the training here. And this is the model that we saved for you. If for some reason you want to evaluate the model on the test data, that should still work. You could say model, evaluate generator, and then pass in test image generator, run that, and you should get similar results as what we're about to get. Keep in mind, depending on the actual shuffling of the training data and the random initializations, this could look slightly differently from what we have here, but overall, you should get something in this range. If we say model.metrics names, it's loss and accuracy. Your accuracy should be somewhere between like 85 and 95%, which is pretty good considering that base accuracy is 50%. Okay, so we'll go ahead and load the model since we don't want to kind of spend all this time retraining the model that we already provided for you. If you are interested in the actual history of this .h5 file, you can check it out in the actual provided notebook. Here we actually show the full history of that training of that model. Okay, so there's the model for you. Coming up next, we're going to basically talk more about evaluating the model, not just the history, but predicting on new images, classification reports, etc. We'll see you at the next lecture.